This conference will now be recorded.
So I was telling you about drug excipient interaction. Now, looking at what happens after the interaction, we should also know what are the possibilities which happens after the interactions. So I was telling you, it can result in the formation of the new impurities, which can be an unwanted impurities, or it can result in incomplete balance. That's what I was telling you. When you know this many amount of excipient, this much amount of excipient you are added, the product whatever you should get also be equivalent to that. So because of the interaction, there is a chance of imbalance. Okay, there's an imbalance with the whatever the ingredients amount you added, you would have not got the expected product out of it. That is called as the imbalance that is called as mass balance. Imbalance, that's incomplete mass balance. So or it can be the destruction of the dosage form because of the drug excipient interaction, or change in the physical chemical properties. When I say physical chemical properties, look into the bracket terms. It can affect the stability, solubility, and dissolution. Also is nothing but the process which is dependent on the solubility, degree of crystallinity, and hygroscopicity. So many physical chemical properties can be disturbed. So remember, whenever the drug excipient interaction happens, there is a chance that it can result in the unwanted impurities. Unwanted impurities might add up, result in the imbalance in the mass balance, or the destruction of the dosage form, or change in the physical chemical properties. Anything can happen. So ultimately it disturbs your stability of the dosage form. So when we focus on the interaction, drug excipient interaction, what are the points we need to keep in mind? So okay, fine, I got an idea about what is the need of drug excipient interactions. Now I need to also look into some of the aspects. So I need to look into the nature of the drug and excipient. I should find out what is this chemical nature or the physical nature of the excipient. And also I should have the knowledge about what is the amount of the drug to be added and what is the amount of the excipient added and at their ratio with each other. Drug excipient ratio. And what is the role of moisture? Does moisture has any influence on the interaction or the influence of the heat, effect of pH of the microenvironment, processing effect, more important. Though when we do the drug excipient interaction normally with the simple glass vase, you may not find any kind of interaction. But the same thing when the processing happens, maybe granulation processing or a mixing processing, there is a chance that processing of the formulation can result in the interaction. And also the influence of the light means we should have the detailed idea, means what all I'm supposed to look into before I actually carry out the drug excipient interactions. So coming to the method, so fine, we got idea now. What are the consequences of the drug excipient interaction? Okay, and what are the criteria we need to look into while carrying out the drug excipient interaction? So let's also understand how we carry out in simple laboratory method, how we carry out the drug excipient interactions. Generally, the same thing is followed in industry also. It's a very simple procedure actually. We need to prepare the blend of drug and excipient. Blend means mixing. So compatibility study is done by blending the drug with excipient at levels that are acceptable to the proposed formulations. So if I am adding the drug one part and excipient one part, so it is 1:1 ratio. So I need to have, that's what I told you, we need to have even the idea about the how much drug and the excipient ratios we are actually including for the formulation. So unnecessary, like I cannot add one part of drug and 10 part of the excipient and carry out the interaction study. It doesn't have any meaning out of that. We don't get any result out of that interaction studies, which you can use it for your need. So we need to keep in mind what is the ratios of the drug and the excipient to be used. And generally it is done by simple blending technique. We are blending the drug with the excipient with acceptable ratio. And for example, just one example has been quoted here. If the lubricant level is 0.5% is required, then 50% drug and excipient mixture is not appropriate. Means when you know that the lubricant level is so less concentration is used, that is hardly 0.5%, then 50% of that I cannot add the more drug or the more excipient and try to carry out the study. So I need to keep that in mind, the ratio also. So do the blending, that is simple mixture. Take the glass beaker or you can take the watch glass, whatever. Take the drug, excipient, mix it with a suitable spatula or with a glass rod and then you subject into accelerated stress condition. So accelerated stability studies also next another important thing means what happens. This reflects the storage condition. Okay, or we can understand the stability of the drug with respect to the duration. I cannot wait for 3 years and the 4 years to come out with the result. So I accelerate the reaction to happen so that at the particular temperature, so that I get the result immediately. So each blend is stored at accelerated stress condition. That's what you would have studied in the B Pharm physical pharmaceutics, accelerated stability studies with respect to the kinetics. That is first order kinetics, second order kinetics, and the degradation, how it happens, which order it follows. So accelerated stability studies helps in minimizing the study time and interpreting the result at the earliest. So this accelerated, the blend is whatever you would have prepared by blending the drug and excipient. It is subjected to accelerated stress condition where you are changing the temperature and the humidity, and then later on you're determining whether your drug is in its normal state or it is changed chemically or physically. So tested for drug substance stability and the drug release after an appropriate equilibrium period. Means I can carry out the stability study, or sorry, drug excipient interaction study before formulation, where I'm just blending the drug and the excipient, or even I can carry out after formulation also, where you formulate it into tablet dosage form and then see during the processing any changes happened, okay, because of the processing parameter. I told you there is many chances that more chances that the excipient interaction may not happen with a normal mixing procedure what we do it by blending, but there is a chance that the reaction can happen during the processing because it will be subjected to the various environmental conditions. So there is a chance that this reaction can be triggered during the processing. So we can carry out the drug excipient interaction study even after the formulations. So this is the simple procedure which we need to follow. Mix the excipient drug of the suitable ratio, subject it to the accelerated condition so that you get the result very quickly. Okay, and then you carry out this either for the that before the pre-formulation, during the pre-formulation, or convert into formulation and subject the formulation to the drug excipient interaction study. So however it wants. Ultimately, we are going to do the excipient, drug excipient interactions. So this is some example. So anyway, this I'll be discussing later on. Thus I'm skipping this slide, not required right now. So coming to the excipient properties, functionality, I told you in the long back in some of the slides. If you go back here, functionality I just highlighted here. It improves the manufacturability or improves the dissolution, viability, all that. This is functional properties of the excipient. So coming to the other properties of the excipient, which you can see list here. For example, what roles they play depending on the dosage form. The solid dosage form, what what role the lactose plays, or the starch, what is that it is used for. So these are the properties of the particular excipients. Those are the functionalities. So by adding this, we can, for example, when I add the lactose, it acts as a diluent, increases the bulk. So it helps in manufacturing aspect. So if I don't add the lactose and I'm trying to actually just add the drug and punch it, it's not possible. Without adding all the ingredients in the tablet preparations, even the diluent or even the binding agents for the preparation of the granules or the so-called as a granulating agent, without adding all that, we cannot just convert into a tablet dosage form. You might have learned as a direct compression method, wet granulation method, or a dry granulation method. Okay, all that is fine. But all the drug cannot be just punched into tablet form unless until you add the required excipients. So manufacturing ability of the particular dosage drug can be improved by adding the suitable excipients. So these are the function, that is what you call the role of the excipients in the particular that solid dosage form. Same thing you can see with the oral liquid dosage forms also, as I was telling you. So when you discuss this drug excipient interaction, no, what we are discussing with respect to your subject is its general overall. We're not specifically concerned, and mainly it is solid dosage form only we are stressing upon, because most of our dosage forms are solid dosage forms. Okay, so we are not deviating from that and understanding the drug excipient interaction with respect to the liquid dosage forms. So don't need to worry. because it's a general thing which we are learning, not very specifically to the any particular dosage form. But since the solid dosage form is one of the major type of dosage form, so many times you see the word as solid. So no need to worry. So coming to the type of drug excipient interactions, so it can be classified into two types. The drug excipient interactions can be of the two types, chemical and the physical. I told you before also, physical change can happen or the chemical change can happen because of the interaction. So now same thing, we are just putting it into the classification. So it can be classified as the chemical interactions or the physical interactions. Hope you are noting down the points, whatever we are discussing in the class, because I told you, we don't expect any ready class notes. So make it a habit of scribbling. Keep separate books, notebook. It's your decision. I will not interfere in that. But make it a point that you note down the points. Okay. So coming to next, when the excipient interacts, drug and excipient interaction happens, the effect can be either positive or negative. The effect can be either positive or negative. In the sense, it can be a positive effect which can be an advantageous, or it can be a negative effect, it can be disadvantageous. So we can also, you can imagine now, many times the drug excipient interaction can be advantageous also, where we expect that the interaction to happen. So positive and negative in terms of the effect on the performance of the dosage form. So the performance of the dosage form can depend on the drug excipient interaction, and that drug excipient interaction can be either positive interaction or negative interactions. So look at the example here. Grinding can cause polymorphic changes or change in the crystalline state that could improve solubility. Just to revise, we know that solids can, powders can exist in amorphous form or in the crystalline form. So amorphous form, usually they have good solubility, but when in those drug product which are crystalline in nature, its solubility depends on another property called as polymorphs. Which polymorph form it is actually. So type 1, type 2, type 3, it is the alpha, beta, gamma. So every polymorph will have a different physical property, but they have the same chemical properties. So if this interaction can change to a particular polymorph, the drug is same. Only its behavior, crystalline behavior is altered. And that altered crystalline behavior has improved the solubility. So that's the positive effect. So we are taking it as a positive drug excipient interaction, which is advantageous for our purpose because it has improved the solubility. Hope you understood the positive effect of the drug excipient interactions. Same thing when you look at the negative, there is a chance that it can affect flowability, stability, packing, or consolidation during compression. So the added excipient, because it is interacting with the drug, it can affect its flow properties. And flow properties are so important, not only with respect to the API, even the blend of excipient, when we blend of drug and excipient we make, no, even that flow property is important. So there is a chance because of some interaction, it can add up negative effect, like it can disturb the flowability. Also, it can disturb the stability. So all these are negative effect of the excipient. So positive effect and the negative effect. So this information is very important for us. So why we do carry out the drug excipient interaction is not just to exclude that excipient, okay, to remove or include. Yeah, of course, I need to do to decide whether I need that excipient or not. And also, if I know that it has a positive effect, maybe I'll be making the decision that, okay, let me keep that excipient because of its advantage. Okay, plus point. So compared to the another excipient which may be competing with the same excipient. I have two, three excipient or two, three disintegrants, for example, or maybe I need to select one out of them. So I need to decide. All three are good, fine. But among the three, which one is best? I need to decide based on this kind of basic information. So this information in the early development phase or at the pre-formulation phase helps in determining the components that will lead to robust and stable formulations. Ultimate goal is to now come out with a stable formulation which is stable during its shelf life. That's our aim, the goal which we need to reach. So let's start with the first one, the physical interaction process. So we just understood about the effect of excipient or excipient interaction. Okay, and we also understood about how to carry out the drug excipient interaction by just simple blending method and subjecting to accelerating condition. Okay, then we also have got idea about what are the functionality of the excipient or its role of the excipients in the particular formulation. Okay, and for what purpose we are adding that excipient, what are its main functions, or like whether it acts as a binder or a disintegrator, all that. Other than that, what functionality it adds up to the dosage form also we got to know. It might increase the enhance the probability, or helps us to go with the proper manufacturing process. All that about are called as functionality. Functions and functionality, they are different. Functions is its role. Functionality means what is that it benefits by adding. What is that we are going to get benefited when we add that particular excipient. That's called as functionality. So coming to the first one, physical interaction, two types of excipient interaction, physical interaction and chemical interaction. Okay, and these interactions can be either positive interaction or a negative, means it can result in a positive effect or a negative effect. So coming to the physical interaction, this physical interaction can happen between the drug and excipient because of the processing also by milling, or it can be the because phase transformation or addition or absorption. It's one example. See, we cannot go in detail each and every interaction, because if I take one drug molecule, one API, and the five excipients, okay, they have their own interaction with each other. Okay, and keeping same five excipients, if I change the drug, for example, again it's a different interaction. So it becomes very difficult for, we are not learning with respect to any particular drug. We are generally learning the importance of understanding the drug excipient interaction. So when I'll be quoting you one or two examples in between, you try to remember those examples. So when you write it in the answer, just highlight those examples to justify your answer. Okay, so let's go ahead. So physical interaction can happen because of many reasons. So the one of the reason is milling and compression. I was telling you, when you just blend together, you may not find any interaction. You may not observe at all. Okay, but when it goes enters into the processing, there is a chance that the interaction can start reflecting. You can start observing that interaction happening. So, any doubt at this point? Anybody have? Before I go with the examples.
No, ma'am.
I just want to know about the flow of the class, how it's like. Is it okay? Can you understand? Or I should go slow? Or it is so dragging that I need to uh, like fasten my presentation? The online class, I understand you need to cope up with the online classes. It's something like new habit. Abhisha, Asha Bisra, Tejaswini.
Yes, ma'am.
Okay, any problem there?
No, ma'am.
हाँ, टुडे आज ठीक है ना? आवाज भी ठीक होगा शायद, नेटवर्क इशू में ये.
हाँ ठीक है मैम, ठीक है.
So okay, let's look into that first. One of the example with respect to the physical interaction which results due to the milling and the compression. The interaction which happens because of milling and compression process. So this is one of the example. I was telling you n number of examples you get to say, read in the textbooks. So metachlopramide hydrochloride has, they observed that during their initial studies, what they noticed is when they were planning for the formulation of metachlopramide hydrochloride into tablet form, so they added the lactose. Okay, and with that lactose, and the lactose, there are different varieties. You can expect amorphous lactose are there. One of the grade of the lactose is amorphous lactose, and they noticed that there is an effect of milling time on metachlopramide because that is it's causing the reaction between the amorphous lactose with the metoclopramide. As the increase, this the reason may be because the increase in surface area produced by milling. Why we do milling? Milling we do actually for mixing up and also for the reduction of the size. So there's the two things which happens there. Mixing also happens. Okay, ball mill for example. Okay, double cone blenders. Okay, these are all used for mixing purpose. And not during the mixing process, there's a chance that the size also will be reduced. When the size is reduced, the increase in the surface area produced by milling as well as amorphous content in the mixture makes the system more sensitive to the pressure and promotes chemical degradation called as Maillard reaction. So they have observed that there is some chemical degradation. It's because of the physical reason chemical degradation is happening. Physical reason is what? It's the milling process. And what is the interaction happening? The interaction is happening between the metoclopramide and the amorphous lactose. And this lactose was added as diluent. So during milling process, they observed there is an interaction happening between these two, and they identified the reason is during milling process, the particle size has reduced, and because of the decrease in the particle size, the surface area has increased, and this increase in the surface area has promoted the chemical reaction degradation by a particular chemical reaction called as Maillard reaction. So that's what they could observe because of the milling. So what they did was annealing of milled sample is done to recover the crystallinity of the drug lost by milling. So this annealing is a process which they have done for the sample so that to avoid this kind of interaction. This is what happens when you know that the interaction is happening, but I want to use that excipient, I don't have a choice. Then I need to find out an alternative. Alternative may be replace it with the compatible excipient. Okay, fine. But I don't have a suitable alternative. So what I can do is I can also look for an other alternative where by adding the same excipient, by some other approach, I can avoid that interaction. So there's something called as annealing of the milled sample. They do the annealing process so that avoids, minimizes, or it is done to recover the crystallinity of the drug lost by milling. So this sentence, I don't know how much you can understand. Loss, crystallinity of the drug lost by milling. So the amorphous nature is actually is the culprit here. The amorphous nature is the one which is actually causing the reaction. So that the crystallinity is lost during the milling process. What happens? Not only that particle size is reduced, even the crystallinity of the lactose is lost, and then that is converted to amorphous form. Because it is converted to amorphous form, it is more prone to react with the metaclopramide. So the crystallinity, you need to minimize the loss of crystallinity without converting it to amorphous form. They do a process called as annealing process. So that's the advantage of annealing process. Just look at the example. Look at the graphical representation of the same. Just observe the graph here carefully. The x-axis is the degradation of metoclopramide with respect to the time. Is the time duration, and this is the metoclopramide. Okay. So they started measuring the amount of metoclopramide after carrying out the process, after the milling process. So first one, the triangle part. I don't know in the mobile if you're visualizing this, if you're seeing through mobile, how clarity it is, I'm not very sure. So there are three lines here. Each line represents different milling time. The first line, this represents actually, one second. This one represents the, that is a square box. The dark color square box represents milled for 15 minutes. Okay. And the second line represents milled for 5 minutes. And the first one represents unmilled, means it's not milled at all. Means if at all imagine that I have mixed metoclopramide with the lactose, if I have not done the milling, after certain duration of the time, there is no much loss of metoclopramide. When I measure the content of metoclopramide by some analytical method, I'll also be discussing later on. Most important part which you need to know is how actually to identify the interaction. So I was expecting these questions from your side actually. So we cannot see everything visually. There should be some analytical method. If color change means okay, I can see the color change, I can say it is interacting. But every time we cannot expect that interaction to happen by change in color. So there are analytical methods we need to depend on which says that okay, there is an interaction happening. So with suitable analytical method, let us imagine they have done three trials. One, they have not they study the drug excipient without milling. Other one by milling for 5 minutes. Other one milling for 15 minutes. They blended metoclopramide with the lactose. Okay, and then they carry out the interaction study after a certain duration of the time. And what they noticed was this unmilled sample means milling has effect. That's what in the previous slide I told you. So here I was telling the effect of milling. If the milling is not done, there is no reduction in the particle size, no increase in the surface area. So there was not much interaction happening with the lactose in the metoclopramide. So there is no much loss of metoclopramide after they measured 10 days or 12 days or 10th hour or 12th hour. Okay, either it is a time or a day. But when it is milled for 5 minutes, they observed that the metoclopramide is drastically decreased because it has interacted with the excipient, which is much more when it is milled for 15 minutes. Means the milling, it proved that for them it became easy to identify that the milling has actually induced the chemical reaction which was happening, and that chemical reaction was the Maillard reaction I was telling you. So milling, still I have not gone into compression, I'm just talking about the milling. This is one of the example we got to know that metoclopramide hydrochloride, when it is mixed with the amorphous lactose, they observed that the milling has enhanced the reaction, and that reaction, chemical reaction, is called as the Maillard reactions. So I was telling you something called as annealing process. So how to overcome that is by process called as the annealing process. I was telling you about this annealing process. So even they have done one more study where they use 3 grades of lactose. See, lactose, I was telling, it can exist in different form, either in the amorphous form, okay, or in the crystalline form. When it is in crystalline form, it can be anhydride form, okay, or a monohydrate form. Crystalline with no water molecule and crystalline with one water molecule. See, I can carry out the experiment however I want to carry out. So this is just for your understanding. I have put the slide to show you that annealing process, the black color bar, there are 3 bar graphs here, and in each category of bar graph, you can see one is the dark shaded. This dark shade indicates the annealing process has been done for the has been carried out during the milling process. So it's an added advantage. So look at the amorphous lactose. Don't look at the rest of the thing. You just look at the amorphous lactose here. So just the amorphous lactose, which was not subjected to annealing process, was used. So what happened? At particular compression pressure, okay, or at a particular compression process, after some time, they observed that with the lactose which is not subject to annealing process is degraded. In the sense, metoclopramide is actually the percentage of metoclopramide is reduced so much that it is almost to the 45%. But the same lactose which is subject to the milling powder subjected to the annealing process, no, the metoclopramide, the same compression process they are applied, but the metoclopramide content still remained almost like a 75% to 80%. Means annealing process, they proved that annealing process can avoid the interaction happening between the metoclopramide and the amorphous lactose when it is subjected to the compression force. Maybe this slide gives a better picture. The next one, I'll just wind up with only one slide. So maybe milling you got idea. Now let me also tell quickly before telling that bar graph, I should have told this. The reactivity increases, okay, because of the compression also. What reactivity we are talking? the reactivity which is caused because of the interaction between the metoclopramide and the lactose, because of the what chemical reaction? Maillard chemical reaction. And that reactivity increases because of milling. We understood with the previous this graph, as the milling time increases, reactivity also increases. Same thing as the compression increases, force, compression force I am talking, the reactivity increases. As the compression increases, the reactivity increases. So reactivity increases with amorphous form of the lactose with the increase among the types of lactose whatever we are using. If at all we are using the amorphous form of the lactose, this amorphous form of lactose is more prone, more reactivity towards the metoclopramide as the compression is increased. So what information it gives us? It makes me to decide, okay, I need to do a process called as annealing process. That's what I did, the annealing process, and I noticed that because of that annealing process, now that interaction is minimized and there is no loss of metoclopramide. Without annealing process, interaction is happening, no doubt, but it results in loss of more amount of metoclopramide. So annealing has an advantage, either because of the milling process towards the milling property, or maybe towards the compression. In either way, it is protecting the loss of metoclopramide. So instead of that, I also get a knowledge that, okay, I can avoid amorphous lactose. Let me use the spray dried lactose or the spray dried lactose monohydrate, which is crystalline in nature. So I can actually avoid, if you look at these two graphs, almost they're closer to each other. Means if at all I'm instead of lactose, if I use spray dried lactose or monohydrate form or a anhydride form, which is crystalline in nature, I can minimize the interaction. So I can avoid the loss of metoclopramide happening because of the interaction. But I'm not telling interaction is completely gone, but it is comparatively much better than the normal amorphous lactose. So if at all you have noted down the points, please revise